Picture a pilot. He's down low, almost skimming the ground, with pine treetops flashing beneath the wing. He's moving so fast the earth below doesn't crawl by, it streaks past in one solid gray blur. And now he has to go supersonic. He reaches for the handle on his left, the one a normal airplane doesn't even have, and the wings of his aircraft begin to sweep back. They move rearward, drawing in toward the fuselage, like a bird tucking its wings before a dive. And somewhere deep inside, behind the calm face, one thought is sitting there, small, cold. What if one wing moves and the other doesn't? That's where we begin today. Not with a blueprint, not with a designer and sleeve garters, but with a simple human feeling you can't write into any logbook. This is about variable sweep wings, about the swing wing, the technology combat aviation on both sides of the Atlantic was obsessed with. The idea was bold to the point of audacity. Let one aircraft do everything. Spread its wings wide, and it can lift off from a short runway, heavily loaded, and stay aloft for a long time. Sweep them back hard, and it can punch through the air at twice the speed of sound. No need to choose. No need to accept the compromise that had tormented aircraft designers for half a century. On paper, it looked like a pure victory of reason over physics. And some of the Cold War's greatest aircraft were built around that idea, ours and the West's alike. Names you've definitely heard: the American F-14, our MiG-23, the huge Tu-160 White Swan. For decades, they flew over half the planet, sweeping their wings in and out. And now the question this whole story is really about: if the idea was so good, why did the world's most advanced fighters walk away from it? Look at the F-22. Look at our Su-57, the peak of combat aviation. Both have ordinary wings, riveted in place, fixed. So where did that brilliant dream go? But before we get to the answer, let's go back to that pilot and his cold little thought. Because the engineers knew about it, and they fought it seriously. Here's the trick with a swing wing. When it pivots, an invisible point inside the airplane shifts, the center of lift, where all the lift is, in effect, applied. The airplane wants to pitch nose down. Its handling changes right in the pilot's hands. And if, God forbid, the wings end up at different sweep angles, one extended, the other swept back, the aircraft will be thrown sideways so violently that at low altitude, survival is almost impossible. The engineers understood that, and on the best aircraft, they locked that danger down tight. On the F-14, for example, both wings were tied together with a rigid shaft, locked together like Siamese twins. Even if the entire hydraulic system fails on one side, the wings physically cannot separate to different angles. One actuator there pushes with enough force to lift about 90 tons, roughly the weight of a loaded railroad coal car. Those are the kinds of forces they had to keep under control so the pilot wouldn't have to be afraid. And they almost beat that fear. Almost. Because fear doesn't live in the metal. It lives in the mind. You can tell a man all day that the shafts and interlocks won't fail, but somewhere in the subconscious, that chill remains. Beneath me is a mechanism that moves while I'm flying. On an ordinary airplane, the wing is dead. It can't betray you. because it doesn't do anything at all. But this one is alive. It turns. It has a mind of its own. And that brings us to the central idea of this whole story. The engineers did something close to impossible. They beat physics. They forged titanium assemblies strong enough to hold the weight of a rail car. They linked the wings so they could not betray the pilot. It seems like they accounted for everything, except one thing. That there would be a human being sitting in the cockpit, a human who gets tired, who in combat has bigger things to worry about than wing sweep angle, and who, no matter how you put it, is a little afraid of the machinery beneath him. So what was variable geometry really? A stroke of genius or a path to a dead end? Was that versatility worth the price they paid for it? In tons of titanium, in reliability, in the pilot's nerves? I'll give you my answer by the end, but I want you to arrive at it yourself. And to understand why they went to all this trouble with swing wings in the first place, we first have to deal with one stubborn fact. There is no such thing as the perfect wing. And for a long time, that meant the designer always had to choose, until at last, he learned how not to choose. To understand why smart people threw themselves into this insane complexity of swing wings, you first have to accept one stubborn truth. The perfect wing does not exist. And that's not because designers were lazy or not smart enough. It's a law of nature. You can't get around it. You can only outsmart it. Take a wide, straight wing, the kind you'd see on a glider or on a good old regional workhorse. Long, stretched out to the sides. At low speeds, that wing is a marvel. It hangs on to the air even when the airplane is barely moving. It can lift a heavy load off a short runway. It's efficient. It lets you fly far without burning extra fuel. And it forgives mistakes. Now let that wing accelerate toward the speed of sound. It stops being your friend and turns into your enemy. The air in front of it starts compressing into a dense wall. Shock waves form. Drag shoots up. The airplane begins to shake, and the control surfaces stop responding properly. A straight wing simply does not let an airplane break through the sound barrier. That is not what it was built for. All right, now sweep the wing back. Sharpen it. Pull it in toward the fuselage. Make it a swept wing. At supersonic speed, that's salvation. And here let me explain why. Because it's a beautiful idea, and it really isn't complicated. Picture the airflow rushing at a wing. If the wing is straight, the flow hits it head-on. But if the wing is swept back, something clever happens. For the wing's leading edge, what matters is not the airplane's full speed through the air, but only the part of that speed that hits across the edge. The speed is, in a sense, split in two. One part slides along the leading edge and does almost nothing. The other pushes across it, and that is the part that really matters. And the more sharply the wing is swept, the smaller that crosswise working part becomes. The airplane may already be flying faster than sound, but the wing, at its leading edge, feels the airflow as if it were moving much more slowly. If you like, the wing is fooling physics. The airplane is beyond the barrier, but locally, across the wing, it is not. That is why shock waves arrive later and weaker, drag drops, and the airplane can pass through the sound barrier without the bone-rattling buffeting that tore up the straight wings of the first jets. So it seems like there's your answer. Give every airplane a sharp, swept wing and call it a day. But the same geometry that saves you at supersonic speed takes revenge at low speed. A sharply swept wing is almost useless when the airplane is slow. It just does not generate much lift. To take off, that kind of machine needs a very high liftoff speed, and that means a very, very long runway. Landing is hard too, fast and right on the edge. And as for hanging in the sky for hours, calmly and efficiently, that is out of the question. See the vice the designer is trapped in? The straight wing rules at low speed and fails at supersonic speed. The swept wing rules at supersonic speed and fails at everything slow. And those two worlds conflict so deeply that, for a long time, they seemed impossible to reconcile. And the military needed both, at once, in one airplane. An interceptor had to launch from a short deck. That was a job for a straight wing. But it also had to race to the target in minutes at twice the speed of sound. That was a job for a sharply swept wing. A bomber had to slip along just above the ground efficiently for thousands of miles, and then punch through enemy defenses in a short supersonic dash. So for a while, designers were forced to choose. They sat down and asked, what do we want more? And what they got was always a compromise. An airplane that did nothing truly well. A little fast, a little long range, neither one thing nor the other. In aviation, there's a handy phrase for that. Neither fish nor fowl. But what if you did not choose? What if you taught the wing to change its sweep right in the air? Spread it out, take off, patrol, save fuel. Sweep it back, go supersonic. One airplane covering both extremes at once. On paper, this was not just a good idea. It was the holy grail of aviation, the dream that solved, in one stroke, the problem that had tortured designers since the beginning of the jet age. There was just one tiny detail left, as usual. Make the wing actually sweep in flight, without killing the airplane and the pilot in the process. And it was that tiny detail that engineers wrestled with for nearly 20 years through dead ends and disasters. And oddly enough, it all began in the ruins of defeated Germany, with a captured aircraft the victors hauled across the ocean. April 1945. The Reich is living out its last days. American troops enter a secret research center in Oberammergau, Bavaria, and among the captured material, they find an unfinished Messerschmitt airplane, the P-1101. It had something no one else in the world had, a wing whose sweep angle could be changed, with one major catch. The angle could only be changed on the ground before flight. Technicians had to reposition the wing by hand. It was still a long way from changing sweep in the air. But it was the seed of the idea, and the Americans took that captured aircraft home to Bell's plant in Buffalo. That seed became the first real step forward. Using German work as a starting point, Bell built the experimental X-5, and in 1951, it did something no one had ever done before. It changed wing sweep in flight. Engineers installed electric motors that rotated the wing panels in the air. The wing had 3 positions. It was a sensation. And at the same time, it was the first serious warning. Because on the X-5, a problem surfaced that would haunt this entire technology right to the very end. We need to stop on that point, because without it, nothing that comes next will make sense. Every airplane has an invisible point, call it the center of lift. That is the place where all the force holding the airplane in the air is, in a sense, applied. And in a normal, well-behaved airplane, that point sits just behind the center of gravity, keeping the aircraft in balance the way feathers stabilize an arrow in flight. Now sweep the wing back. Its entire lifting surface shifts toward the tail. And that center of lift slides backward too, sometimes by yards. But the center of gravity stays almost where it was. A huge moment arm grows between them, and the airplane feels an irresistible pull to drop its nose. It pitches nose down. To hold it, the pilot has to pull back on the stick and deflect the control surfaces. And those surfaces create so much drag that they eat up the whole benefit of sweeping the wing. That was the curse of variable geometry. When you swept the wing, you were not just changing its shape, you were throwing the whole airplane out of balance. And on the early aircraft, that drifting center of lift made them dangerous, temperamental, almost uncontrollable. The X-5 had a vicious streak. At certain wing positions, it could enter a flat spin that was impossible to recover from. One of those spins cost a test pilot his life. Meanwhile, another company nearby, Grumman, remember that name because we'll come back to it, and we'll come back to it in style, was building a carrier-based fighter for the Navy, the F-10F Jaguar. It had a swing wing too, now hydraulically operated, with sweep changing from about 13 to 42 degrees. On paper, it looked great. In hardware, it was a disaster. Handling was awful, and the mechanism was still immature. The program was canceled, and the Jaguar went down in history as one of the worst fighters ever to get off the ground. By the mid-1950s, the conclusion looked grim. The idea was brilliant, no question, but that drifting center of lift killed it at the root. The swing wing was a beautiful dream that in practice turned an airplane into an uncontrollable beast. A lot of people wrote off the whole concept and went back to conventional wings. And they would have been right, if not for one laboratory where at that very moment, quietly, without fanfare, engineers were running models through wind tunnels. And there, in that silence, a solution was taking shape that would change everything. A solution so simple and so clever that when you hear it, you'll probably say, "That's it? Then why didn't they think of that from the start?" Why it took 20 years to get there, that's what we're about to talk about. The solution was born not in the cockpit of some heroic test pilot, but in the quiet of the research center at Langley. For years, engineers ran swing wing models through the tunnels and wrestled with that same drifting point. And at some point, they asked themselves a question that was almost childishly simple. Why are we rotating the entire wing around a pivot right next to the fuselage in the first place? Here was their insight. Before that, the hinge, the axis the wing rotated around, was placed right up against the fuselage. The whole wing turned, all of its area at once. And so, when it swept back, that entire area shifted toward the tail, dragging the center of lift with it. Logical and fatal. But what if you moved the pivot axis outboard, away from the fuselage, off to the side, closer to midspan? Leave part of the wing root fixed as a triangular wing glove. Then let only the outer wing panels rotate, mounted on that outboard pivot. And that's when a small miracle happened. Once the axis is moved outward, sweeping the wing back sends one part of the wing aft, while another part, relative to that axis, effectively moves forward. the two shifts cancel each other out. If you calculate the pivot location precisely, the part of the center of lift shift caused by sweep almost disappears. The point stays put. The airplane does not pitch nose down. The curse is broken. That was the central secret behind every successful swing-wing aircraft. Not the fact that the wing could sweep. Engineers already knew how to do that. The real breakthrough was the correctly positioned outboard pivot, combined with a fixed wing glove at the root. That discovery at Langley turned a crazy dream into working technology. Without it, there would have been no Tomcat, no Tu-160, none of the aircraft we're here to talk about today. This is the turning point of our whole story, and as you can see, in the most literal sense. So that should have been it. Problem solved, time to build. But the moment engineers fixed one problem, they created another. And this one was much heavier. Literally heavier. Think about it. Before, you could at least try to rotate a relatively light wing right at the fuselage. But now the entire colossal force from the outer wing panels, all the lift, all the wing bending load, is transmitted through a single point. Through the outboard pivot. Through the axis carrying, without any exaggeration, the whole aircraft. And the forces there were monstrous. In a hard turn, a fighter's wing can carry a load 7 or 8 times the weight of the airplane itself. And all of that, tens of tons, presses, tears, and twists one single assembly. And it has to survive that hundreds of thousands of times over the life of the aircraft, without a single crack. Because the tiniest fatigue crack there means the wing tears off in midair. To carry forces like that, engineers needed a component they called by different names, but the idea was always the same. Running across the fuselage from side to side was a massive carry-through structure, a closed titanium box that tied together the pivots of the left and right wings. It was both the heart and the backbone of the entire aircraft. The bending load from one outer panel had to be transferred through the fuselage to the other. Otherwise, the airplane would simply fold in half. And that box, as we'll see later in specific aircraft, turned out to be monstrously heavy and monstrously expensive. And that is exactly where the trap lies, the one we'll keep coming back to throughout this film. In a conventional wing, strength is spread throughout the structure. In a swing wing, everything depends on a single assembly, one point. And if that point fails, it won't just be one part failing, everything fails. The engineers understood that. They built that assembly with a 10-fold safety margin, tested it, backed it up with redundancy. They were sure they had accounted for everything. Right up until the day when, over an American test range, the wing on one such aircraft folded on its own, without any command from the pilot, due to metal fatigue. The 1960s. Armed with the solution from Langley, the U.S. military launched an extraordinarily ambitious project called TFX. The idea was bigger than just a swing wing, one universal aircraft for both the Air Force and the Navy, a strike aircraft and an interceptor. Different missions, different requirements, and all of it was supposed to be reconciled in a single airframe. How? With a wing that could change its shape. The contract was signed in December 1962, and in December 1964, the aircraft made its first flight. That was how the F-111 was born, the world's first production aircraft with wings that could sweep in flight. It was a giant. Its wings spread wide for takeoff and swept sharply back for a dash just above the ground. It could cover hundreds of miles in nap-of-the-earth flight, in darkness and bad weather, following the terrain by radar. For its time, this was a weapon from the future. And in the F-111, you can clearly see how the swing wing stopped being a trick and became the core of the entire design. The idea itself was bold to the point of audacity. One basic aircraft would meet the needs of both land-based aviation and the Navy. On paper, the savings looked enormous. One airplane instead of two. But everything has a price, and the first price was weight. That same titanium carry-through box holding the pivots for both wings turned out to be incredibly massive. The calculations showed that the wing itself, because of the sweep mechanism, became roughly 1/5 heavier than a conventional wing of the same area. And the aircraft's empty weight went up by several percent overall, just for the privilege of folding the wings. That extra weight ate into everything. It ate into fuel, ate into bombs and missiles, and hurt acceleration. The engineers gave the airplane the freedom to change shape, and immediately strapped a lead backpack onto it, one it had to carry for its entire life. In the end, the Navy gave up on its version altogether. For carrier use, the aircraft came out too heavy and too bulky. The universal dream showed its first crack. And as it turned out, the word crack here was not a figure of speech. 1969. A training flight over the test range near Nellis Air Force Base. In the air, the wing attachment assembly on one F-111 failed. The engine didn't fail. It didn't run out of fuel. The structural part holding the pivot broke. The wing folded not on the pilot's command, but at the will of metal fatigue. The crew was killed. The investigation uncovered something terrifying. One of the attachment components had contained a microscopic crack from the factory, a defect in the metal, less than ½ an inch long. Not a single inspector spotted it, and under flight loads, that tiny crack grew, and in one instant, severed the assembly carrying the entire wing. Remember what we said? With a swing wing, everything depends on a single point? This is exactly what that means. The downside of a brilliant idea. Where a conventional wing spreads its strength throughout the structure, here the life of the whole aircraft hangs on one assembly. And the price of an error there is not damage, it's life. The entire fleet of these aircraft was grounded immediately. And the engineers came up with an inspection that was harsh, almost brutal. Every wing on every airplane was put into a test rig and chilled down to deep freeze temperatures. Because in the cold, metal becomes brittle. And if a hidden crack is lurking inside it, the assembly will fail right there on the test stand, on the ground, under the press, instead of in the sky with a pilot aboard. That cold test became a required ritual for years. That was the price of universality, paid not on paper, but in blood. And still, this was only the first try. Because one company took all those bitter lessons and turned the swing wing into a true masterpiece. You already know that company. The same one that had once embarrassed itself with the Jaguar. If the F-111 was the first try, uneven, partly flawed, Then the real masterpiece of the swing wing was the aircraft you've almost certainly seen in the movies, the F-14 Tomcat. And it was built by that same company, Grumman, the one that had once stumbled with the Jaguar. It absorbed every lesson and created perhaps the most refined swing-wing aircraft in history. The Tomcat was the Navy's carrier-based interceptor. Its job was to launch from the rolling deck of an aircraft carrier, race out hundreds of miles toward a target, deal with it, and come back home to that same deck. And that is exactly why the carrier deck loves the swing wing. An aircraft carrier is an airfield only a few hundred feet long, and on top of that, it's moving with the waves. To get off a strip like that, and above all to come back to it, landing at the lowest possible speed, an interceptor absolutely needs a wide, fully spread wing. Miss your landing speed, and you go either into the water or into the stern. But that same interceptor also has to fly toward the enemy at twice the speed of sound, and for that, it needs a wing swept into a sharp arrow. Without variable geometry, reconciling those demands was almost impossible. The Tomcat solved the contradiction with a single motion. Now let's look inside. In normal flight, its wing sweep varied from 20 to 68 degrees. And what was especially elegant was that the pilot did not have to think about it at all. On board was a computer that smoothly selected the proper angle based on speed and altitude, then moved the wings on its own. Remember that chill from the first part, the extra burden on the pilot? Here, the engineers took that burden off the person and handed it to the machine. If you wanted, you could take control yourself, but in combat, the airplane did it all automatically. There was also a special position, oversweep, up to 75 degrees. You couldn't use that in flight. The wing would start to interfere with the tail. That was only for the ground. By sweeping the wings beyond their normal limit, the Tomcat tucked them close to the fuselage and took up less space in the cramped hangar below deck. And down there, on a packed aircraft carrier, every foot was worth its weight in gold. So what was a machine like this made of, one that had to carry such loads? Nearly a quarter of its entire structure was titanium. Not aluminum, but expensive titanium. Difficult to work with, temperamental in manufacturing, yet fantastically strong. The pivots were made from it, the wing skins were made from it, and so was that carry-through box across the fuselage. And that box was welded from titanium with an electron beam in a vacuum. For its time, a technology that was almost space age. And there's one more subtle detail that enthusiasts love. When the wing pivots, a gap opens up between the movable wing panel and the fixed wing glove. And at supersonic speed, any gap means turbulent flow and extra drag. So they built retractable triangular surfaces into the glove. At high speed, the automation extended them forward, and they neatly redistributed the load, helping the airplane stay in balance. A small detail, and so much intelligence packed into it. The Tomcat was the peak, and it wasn't alone. Across the Atlantic, the swing wing grew into its most imposing form of all, the B-1 Lancer strategic bomber. Its wing sweep changes from 15 to almost 68 degrees. The logic is the same. Wings out, and it cruises efficiently over huge distances. Wings swept back, and it punches through defenses down low with a short, supersonic dash. A bomber needs two things that seem to cancel each other out: range and penetration speed. The swing wing gave it both. And in Europe, 3 countries, Britain, Germany, and Italy built the Tornado together. And in many ways, this was the last major combat aircraft in history with a swing wing. After it, nobody seriously came back to the concept. The Tornado even had one elegant little detail. The weapon pylons under the movable part of the wing were made to pivot too. They rotated with the wing, so bombs and missiles always stayed aligned with the airflow. Think about that. To make a swing wing work with externally carried weapons, engineers had to make not just the wing pivot, but the pylons under it as well. Complexity breeds complexity, and we'll come back to that idea. That's the Western school of swing wing design at the height of its craft. Now let's jump to the other side of the ocean, because the Soviet Union built its own school too, in some ways cleverer and more economical than the Western one. And characteristically, it didn't start from a blank sheet, but from one very thrifty, very smart idea. In the Soviet Union, work on variable geometry began almost at the same time as it did in the United States. And on July 9, 1967, at the air show in Domodedovo outside Moscow, the public got its first look at two brand-new swing-wing aircraft at once, the Su-57 and the MiG-23. Western attachés were sitting in the stands too. To put it mildly, the impression was strong. The Su-57 deserves a special bow for sheer cleverness. It was the first Soviet variable geometry aircraft and the first aircraft of this type anywhere in the world to be built in a truly large production run. But the most interesting part is how they did it. At the Sukhoi Design Bureau, they didn't start drawing a brand new airplane from scratch. They took the already proven and successful Su-7 fighter bomber with its conventional wing and converted only the outer wing panels to pivot. Take in how elegant that move was. On the Su-57, not the entire wing moved, only the outer panels. The inner root section stayed fixed. And that solved several problems at once. That same old issue of the shifting center of lift became much less severe. If only part of the wing moves, the balance shifts less too. Under the fixed root, the guns, hardpoints, and landing gear remained in place, and the redesign cost nothing like what a whole new airplane would have cost. For all that benefit, the aircraft gained only about 880 pounds. By swing wing standards, that was next to nothing, a very modest price to pay. A synchronizing shaft running through the fuselage and around the intake duct on universal joints kept the left and right wing panels moving in sync. The logic was the same as on the American designs: no independent motion. The wings were rigidly linked and moved as one. The MiG-23, though, took a different path. On that airplane, almost the entire wing pivoted, and it was a full-fledged front-line fighter. It had three main positions: 16 degrees, wings out, for takeoff, landing, and long-range flight, 45 for maneuvering, and 72, wings fully swept, for supersonic flight. A dual-channel hydraulic motor drove the system, and jack screws converted that rotation into movement of the wing panels. But on the MiG-23, our old familiar problem showed itself in full force: the shifting center of lift. During wing sweep changes, the airplane's behavior changed noticeably, and the pilot had to anticipate it. It's no coincidence that, over time, the designers added another intermediate setting, a little over 30 degrees, specifically for combat maneuvering. That's direct evidence of how engineers were fighting for balance. hunting for compromise angles. Hold on to that thought. We'll talk about the MiG-23's character separately, and it won't be a cheerful conversation. The Soviet Union applied the same logic to the Su-24 frontline bomber as well, an airplane similar in concept to the American F-111. Its wing sweep changed from roughly 16 to 69 degrees, and its drive system was dual-channel and reliably redundant. The Su-24 could do the same things as its counterpart across the ocean, sneak in low and break through defenses at speed. And it paid the same price for that, in weight and complexity. But the ultimate monument to the swing wing is, of course, the Tu-160, the White Swan. The largest and heaviest combat aircraft in history, and still one with a variable sweep wing, changing from 20 to 65 degrees. Wings out, and it cruises efficiently over immense range. Wings swept back, and it goes supersonic. Empty, it weighs about 110 metric tons, and nearly a third of that weight is titanium. Its structural backbone is a fully welded titanium carry-through box running across the entire fuselage. And now, here's the number that puts a period on this whole discussion. The wing pivot assembly alone, the spot the outer wing panel rotates around, weighs about 6 metric tons per side. 6 metric tons is the weight of more than one passenger car. One part, just so the wing can swing. That's more than some light airplanes weigh in total. There it is, the physical price of our brilliant idea, cast in titanium. And once you keep that number in your head, 6 metric tons for a single assembly, you start to understand why, at some point, engineers around the world began asking an uncomfortable question. Is it even worth it? But the highest price for the swing wing wasn't paid in metal. It was paid by the person in the cockpit. And that's what we need to deal with for real now. We've spent a long time talking about titanium, pivots, 6 metric tons, and that shifting point. Those are all cold numbers. But inside the cockpit of every one of these machines sat a living human being. And in the end, that human being made the swing wing pay the highest price. The thing is, variable geometry gave the pilot one more job, one more thing to worry about, on top of 1,000 others. Pilots have what's called a scan. Non-stop, in a loop, their eyes move across the instruments and the sky. Airspeed, altitude, attitude, gun sight, enemy, fuel, back to the enemy. That loop is already close to the limit of human capacity, and the swing wing inserts one more mandatory item into it. What sweep angle is the wing at right now? Is that angle right for this speed? Is it time to change it? On the best aircraft, like the Tomcat, that burden was handled by the automatic system. But that system wasn't everywhere, and it wasn't always fully trusted, so manual mode stayed in reserve. And where the wing had to be moved by hand, it became one more burden on an already overloaded person. And this is the right moment to talk about the airplane that was called, behind its back, both a pinnacle of engineering and a treacherous machine. The MiG-23. A fast airplane, and for its time, a formidable one. But in service, it earned a reputation as an exacting, demanding aircraft that was unforgiving of carelessness. Let me say this clearly and honestly, without exaggerating. It would be wrong to blame all of its troubles on the swing wing. There were many causes behind its accident rate, and the airplane itself won over plenty of pilots. An American pilot who flew a captured MiG-23 for years said he had never met anyone who didn't fall in love with the machine. But the fact remains, the MiG-23's accident rate was one of the highest in the Soviet Air Forces. At low speeds, it could be temperamental, and it demanded a pilot of the very highest skill. And part of that unforgiving character was the price of the movable wing itself. When the sweep changed, the balance changed, the airplane's behavior changed, and the pilot had to feel that almost instinctively and stay ahead of it. It was as if the airplane changed its character a little, depending on how the wings were set. For an experienced ace, manageable. For an average pilot, especially in the heat of combat, one more chance to make a mistake. And in an airplane like that, mistakes were expensive. And now, back to the fear we started with. Asymmetry. Every swing wing pilot knew somewhere deep down, those wings move. Which means, at least in theory, they can move the wrong way. One side moves, the other jams. Then what? Lift becomes unequal from one wing to the other, and the airplane instantly and violently banks and yaws. At speed, that means an almost immediate, uncontrollable roll. As we've seen, engineers fought that fear with everything they had. They linked the wings with a common shaft, added redundant hydraulics, and made asymmetry mechanically impossible. And technically, they almost conquered that nightmare. Almost. Because fear doesn't live in metal. It lives in the mind. No matter how many times you tell a person that the shafts and interlocks won't fail, there's still that cold thought in the back of the mind. Beneath me is a mechanism that is moving while I fly. And that a machine really can take on a life of its own was proved one day by a case that still sends a chill down your spine. In the summer of 1989, a MiG-23 in Europe suffered a failure during acceleration and was left without a pilot. The pilot ejected. And the airplane, empty, with no one in the cockpit, kept flying on its own. More than 560 miles across several borders until it crashed in Belgium, killing a person on the ground. Yes, that story was not directly about the swing wing, but the image it left was terrifying. A machine flying by itself, of its own will, not asking humans for permission. And that's when the full picture comes together. On one side, the engineers, who did something almost impossible. They beat that shifting point with the outboard pivot. They built a titanium carry-through box that could hold tens of tons. They linked the wings so they could not betray the pilot. It seems they accounted for everything. On the other side, the human being. The one who gets tired. The one who, in combat, has no spare attention for wing sweep angle. And the one who, no matter how you slice it, is a little afraid of the thing moving under his feet. Engineers gave him the freedom to change the shape of the airplane, and with it, handed him one more variable in an equation he was already solving at the edge of his limits. And when it became possible to give the pilot the same speed, the same maneuverability, but with a simple, fixed, reliable wing, one he didn't have to monitor and didn't have to fear, how else could this argument end? We'll get to that next time, and the answer may surprise you. So let's add it up honestly. On one side of the scale, everything the swing wing gives. On the other, everything it takes away. On the cost side of the scale, the load is heavy. Weight, We've already seen the Tu-160's 6-ton pivot and a wing that's about 20% heavier than a conventional one. Complexity. Hydraulic motors, shafts, actuators, seals, hundreds of parts in the most heavily loaded part of the aircraft, and any one of them can fail someday. Money. All of it has to be made from titanium, inspected, checked for flaws, run through test stands. An airplane like that costs more to build and more to maintain every single hour it's in service. And ask an ordinary squadron technician. To him, a swing wing means dozens of extra points that have to be inspected, lubricated, and replaced, while a conventional wing asks for none of that. And on the benefit side sits the whole reason this began in the first place: real, undeniable versatility. The Tomcat really could launch from a carrier deck and really could chase down targets at nearly twice the speed of sound. The Tu-160 really does have the range of a strategic bomber, and it really can make a supersonic dash. These aircraft did things no fixed-wing airplane of their generation could do. That's not hype. That's physics. And it worked. So which side wins? In the 1960s and 1970s, clearly the swing wing did, because engineers simply had no other way to reconcile short runway takeoff with flight at twice the speed of sound. The trade-off was worth it. Weight and complexity were an honest price for a capability that otherwise did not exist. But technology doesn't stand still, and while Tomcats and MiGs were carving up the sky, a few developments were quietly maturing in the labs. Developments that made the whole swing wing idea not bad, but simply unnecessary. First, aerodynamicists learned how to get excellent maneuverability and good takeoff performance from an ordinary fixed wing, using special leading-edge root extensions. They're those sharp beaks at the base of the wing you see on the F-16 and the F-A-18. At high angles of attack, they shed a powerful vortex that sharply boosts lift. And that delivered a good share of the swing wing's advantages, without a single moving pivot, without a 6-ton titanium joint. Second, fly-by-wire arrived, when a computer sits between the pilot's stick and the control surfaces. Before that, an airplane had to be inherently stable, or a human pilot simply couldn't hold it. That's why everyone feared that shifting center so much. Now, stability is handled by a computer making dozens of corrections every second. The airplane can be designed deliberately unstable and insanely agile because of it, while the computer keeps it under control. The main reason to fear that shift in balance disappeared. Third, engines became vastly more powerful, and their nozzles learned to deflect, steering the exhaust stream. When engine thrust exceeds the aircraft's weight, the machine accelerates and turns almost on engine power alone, no longer depending so heavily on the perfect shape of the wing. And you know, the swing wing wasn't even the boldest attempt to outsmart nature. They tried something even more exotic: the oblique wing. The idea was almost crazy. One single feather-like wing rotating as a whole, like a compass needle, with one panel sweeping forward and the other back. In theory, it was even more efficient, and it needed only one pivot. But an asymmetric wing made the aircraft roll and yaw at the same time in the most unnatural way, and without modern electronics, there was no way to manage it. The oblique wing remained a wind tunnel curiosity. And that's an important lesson. The swing wing was the best of an entire family of transformer wings. And if even the best of them ran into a wall, then the problem wasn't execution. It was the whole idea of changing geometry with hardware. And now, in this next-to-last part, I can finally answer the question I raised at the very beginning. What was variable geometry? A stroke of genius or a dead end? My answer is both at once. It was a brilliant dead end. Brilliant because engineers really did solve a problem that looked unsolvable and gave aviation 2 decades of extraordinary machines. A dead end because that road was overtaken. It's not that the swing wing turned out to be foolish. It's just that another road was built beside it, shorter, lighter, and more reliable, and the old one emptied out. If stories like this, stories about engineering truth without the polished gloss, are your thing, subscribe. We've still got a lot to talk about. And before the curtain falls, there's one last question left. If the idea really was that good, why do the most formidable fighters on the planet flying right now get along just fine without it? Look at the most formidable fighters on Earth. The American F-22 Raptor, our Su-57. These are the peak of combat aviation, 5th-generation machines. And do you know what they have in common? Both have an ordinary fixed wing. No folding, no pivoting, not a single hinge. So where did that brilliant dream go? The one people fought so hard over? Now we have the full answer. They simply don't need it. Other technologies do the job now, the ones we've already talked about. Fly-by-wire, which lets them be deliberately unstable and therefore highly agile. Powerful engines with thrust vectoring nozzles. Clever aerodynamics from leading-edge root extensions. Everything engineers once needed a movable wing to achieve is now done another way. Lighter, cheaper, and more reliable. But there's one more reason too, and for the new generation, it may be the biggest one. Stealth. These aircraft are built around low radar visibility, and a swing wing is an absolute nightmare for that kind of airplane. Moving joints, gaps between the wing and fuselage, open recesses, a large metal pivot. All of it reflects radio waves brightly and lights up on radar like a bulb. To hide an airplane, its surface has to be smooth and continuous. A fixed wing hides easily. A swing wing hardly can at all. Put it all together, and the verdict is clear. A swing wing offered unique capabilities only as long as there was no other way to get them. Then came electronics, more powerful engines, new aerodynamics, and the demand for stealth. And suddenly, every advantage of the movable wing had a lighter substitute. But the downsides, weight, complexity, cost, radar vulnerability, and extra workload on the pilot never went away. The cost side of the scale stayed heavy. The benefit side emptied out. And here's the last thing that really matters. This technology did not fail. It was not a mistake. The F-111, the Tomcat, the MiG-23, the Tu-160, these were not dead-end monstrosities. They were brilliant answers to the questions of their time. The swing wing was an ingenious bridge across a gap that couldn't be crossed any other way. And then engineers built another bridge beside it, shorter and stronger. So the old bridge was abandoned. It didn't collapse. It was simply left behind. Now picture yourself standing next to one of those machines. A Tomcat on the deck, tucking in its wings. A white swan changing shape right in front of you in flight. Think of the engineers who did everything they could to make that machine perfect. Think of the 6 tons of titanium in a single assembly. And think of the person in the cockpit. The fatigue, the concentration stretched to the limit, and that quiet chill that comes from a mechanism moving beneath him in the sky. Because in the end, aviation is driven by more than the laws of aerodynamics alone. It is driven by people. And even the most perfect machine still runs up against one simple truth. There is a human being sitting in the cockpit. For all their brilliance, that is the one thing engineers never manage to calculate in pounds and degrees. And I've given you my answer today. Now it's your turn. Is the swing wing a monument to human ingenuity? Proof that we managed to outsmart physics itself? Or is it a monument to our eternal weakness? The way we love solving one hard problem by creating 10 more. Let me know in the comments what you think. And let the Raptor and the Su-57 keep flying on their quiet, dead, reliable wings. Wings that do not move and do not need to be feared.